Okay, hello everyone. My name is Dmytro Heleshko, and in today's weekly paper review, I present to you a paper titled Score Jacobian Chaining, Lifting Pretrained 2D Diffusion Models for 3D Generation. To be extremely short, it's like an image diffusion combined with NeRF, but instead of neural radiance field, it outputs voxel radiance field. To be a bit more specific, let us refer to the abstract and see what authors have to say. They state that the diffusion model learns to predict a vector field of gradients, and the authors propose to apply chain rule on the learned gradients and backpropagate the score through a differentiable renderer. There are different kinds of models that try to achieve the same goal. For example, 2D supervised 3D GANs, neural radiance fields, clip-guided, and optimization-based 3D generative models. Unlike all of those, this particular model can be run on top of the already pre-trained off-the-shelf 2D generative model, such as Stable Diffusion. It outputs voxel radiance fields, and querying voxel is a simple memory operation that is much faster than the feedforward pass through a neural network. And unlike clip-guided, it does not require to use a guidance from a pre-trained image-to-text model, and instead it uses an already a more proper 2D generative model, which is an image diffusion model. Many prior works perform 3D generative model by training on 3D datasets, and this approach is challenging and format ambiguous because there is no universal format. There are point clouds, there are meshes, radiance field, and etc. What is common to all of those 3D assets is that they can be rendered in 2D. Here we will begin to discover more details about the realization. The idea is that the image may be parameterized by some function with parameters, and there are many potential use cases for pairing a pre-trained diffusion model with a different choice for a function. As stated previously, the algorithm can be run on several off-the-shelf diffusion models, and in our case, the function is a volume rendering function, and the parameter is the desired 3D asset. So this setup aggregates the 2D scores from multiple viewpoints and aggregates it into a 3D score. And this way, the model is repurposed for 3D data generation instead of 2D image diffusion. Yes. The 3D scoring. Now, there's a bit of math regarding 3D scoring, which I will not cover because of reasons. But the main point is that we assume that the probability density of 3D asset is proportional to the expected probability densities of its 2D image renderings. And you can see the formula presented on the slide, that the 3D score is calculated from 2D score, which we get from a pre-trained image diffusion model, and renderer Jacobian. The 2D scoring, we get the 2D scoring from the pre-trained image diffusion model. Yet here lies the main technical challenge. That is the distribution mismatch when computing the 2D scores on non-noisy images. As you can see on the figures, when we try to merge the blob and the face, in the first example, it does not merge successfully, and in the second example, it does merge. So the technique called pair trap and average scoring is the main contribution of this paper. It computes the score on non-noisy images with a denoiser by adding noise to the input and then considering the expectation of predicted scores with respect to random noise. In practice, Monte Carlo estimate of expectation is used. It's funny that authors added a very simple explanation for a clueless reader. As you can see on the image, they say that they add some random noise to the x subscript pi, then they find the blue points, brown lines, and they take the average. The authors say that the voxel radiance field is a powerful representation of 3D asset, but when using it, the model may cheat in a number of different ways. So they use different regularization strategies. The first one is emptiness loss with schedule. Ideally, the space should be sparse with near zero densities except the object, and hyperparameter lambda is used to control the contribution of the emptiness loss. Because if we use too much of this loss in the early stages, it will hinder the model's capabilities of learning the 3D structure. And if we use too little of this noise, then there will be a lot of density artifacts around the object, as you can see on the images from left to right. Another type of regularization is center depth loss, which is used so that the objects will be created in the center of the scene instead of wandering to the borders of the image. Authors also tried comparing annealed and random noise for 2D image sampling with their perturb and average scoring. The random noise schedule exhibits strong mode-seeking behavior, but may result in low-quality images. It works best when image is conditioned on the prompt and the guidance scale is high. For example, when we use this algorithm on top of the image diffusion model that is trained on a small data set, or when the language prompts are not used, then we have to carefully design an annealed noise scheduling. The main alternative or an adversary to this network is a dream fusion. The authors have read their paper and they adopted a couple of ideas. The first one is the randomized scheduling of noise, and the other one is the view augmented language prompting that improves the overall 3D quality. Those are, for example, the language prompts that are in front of, the backside of, overhead view of, and etc. They also add the position of the camera and its direction into the prompt too. The scene itself is a voxel grid of size 100 by 100 by 100 and is placed at the world origin with a normalized side length. We sample cameras uniformly on a hemisphere that covers the voxel cube with a radius of 1.5, with a look at direction pointing at the origin. The camera field of view is randomly sampled from 40 degrees to 70 degrees during optimization and fixed to 60 degrees at Thames time. The same technique is reported to be used in Dream Fusion, and they found that this FOV jittering can help during 3D asset optimization. Here is the visualization of 3D assets, which are created using Stable Diffusion. And it is worth mentioning that this particular model is not a very consumer-friendly piece of technology, because it can take up to 9 gigabytes of GPU memory when optimizing a single asset. But it is certainly a step into the direction of 3D asset generation from a language prompt. In conclusion, the authors proposed an optimization-based approach to generate 3D assets from a pre-trained 2D image diffusion model. The main contribution are the implementation of perturb and average scoring method, which bridges the gap between the denoising trained diffusion models and the non-noisy images encountered in the process of optimizing a 3D model guided by the diffusion, and the new regularization laws for improving the quality of generated 3D scenes. That's all. Thank you.